Good evening, all. Welcome to the last session for the live sessions on NPTEL for Thermodynamics course. So we'll wait for a couple of minutes and then we'll get started. So we stopped in the last class on we discussed on what for Rankine cycle problem, and then we also discussed the problem on refrigeration cycle, but then we didn't discuss on Brayton cycle. So we'll solve a couple of problems on Brayton cycle, and then we'll wind up the session for this week. So this is the last session that we'll be having for this particular course. We'll wait for a couple of minutes for more students to join, and then we'll get started. Just share my screen. You can go through the problem in the meantime and attempt it yourself. You can attempt problem number 7. This is where we stopped in the last week. So we have a single heater regenerative cycle. The steam enters the turbine at 30 bar, 400 degrees Celsius, and the exhaust pressure is 0.1 bar. The feed water heater is a direct contact type which operates at 5 bar. Find the efficiency and the steam rate of the cycle. The increase in the mean temperature of the heat addition, efficiency, and steam rate as compared to the Rankine cycle without regeneration. Pump 1 can be neglected. A bit of involved problem. So if I were to draw the schematic, so how would it be? So I have a turbine. And the output of the turbine goes to the condenser. Let's say this is my condenser. And from the condenser, what happens? It goes to the pump. Let's say I put my pump here. So what happens here? So previously when we were solving, so this is your pump and then you have your boiler. This will be your boiler and everything will be connected with each other. Give me a second. I think there is some issue with the software. Okay, so from the condenser, you'll have another connection that goes to the pump. And from the pump, it will go to the boiler. And from the boiler, it will again go to the turbine. This is a normal Rankine cycle without any regeneration. Now what happens in regeneration? So what happens in regeneration is a part of the turbine outlet which is actually going to the condenser will actually be used so that this whatever is output of your turbine will be at a high temperature. So what we want to do is use this high temperature one so that you can reduce the amount of heat you supply to the boiler. So we introduce something called a heat. This is my boiler. So I'll introduce a heater in between. And what does this heater do? It will take the output from the turbine. So the output of the turbine will go into the heater, and from the heater it will again go into another pump. So this whichever is directly going here will now be connected to the heater over here. And from this heater you will have another pump. And this pump will get connected to the boiler. So what happens now is previously whatever you are supplying to the boiler is directly going from the pump. This heater is not there. So what we are doing now is we are taking a portion of the outlet from the turbine, which is at a high temperature. So the amount of heat that you have to supply in this heater will actually be less than the amount of heat you will be supplying in the boiler. So this reheated one, when it goes to the boiler, will be at higher temperature. So the temperature difference across the boiler, like inlet and outlet, is getting decreased. So since the temperature difference is decreased, the amount of heat supply will also get decreased. So this is the advantage you'll get. But then the disadvantage is because only a part of the turbine, like part of the turbine is sent here and the remaining part is actually going here. So whatever is the power output of the turbine, you say the power output will actually get reduced here because the mass flow rate is reduced. So the net power output will also get reduced. So this is a trade-off that you have to balance. So there will be a reduction in the total power output, but then there will be a reduction in the amount of heat supplied also. So the efficiency can actually be higher or lower depending on that ratio, and that ratio is what we'll see that you can express in terms of the increase in the mean temperature. So we'll calculate that in this problem. So let's put the state numbers here so that it will be easy for us later. So let's say the inlet of the turbine is state 1, and whatever is going into the heater we'll call that state 2, and whatever is going out of the turbine to the condenser we'll call it state 3. The output of the condenser, let's call state 4. The outlet of the pump we will call state 5. So both of these are going inside, and the outlet of the heater we will call 6. The outlet of this pump we will call 7. And the outlet of the boiler is again state 1. So now I have identified all the states. Now let's write down the properties that are given to us. So what is given to us? So it says that the steam enters a turbine at 30 bar and 400 degrees Celsius. So which means P1 is 30 bar and T1 is 400 Celsius. Or if you would like convert it to Kelvin, you can convert it to Kelvin. And what else is known? The exhaust pressure. Exhaust pressure is a pressure outlet of your turbine, that is P3. So P3 is also given as 0.1 bar. Do I know the value of P3, which is something that is not provided here directly? And then I also know that the feed water heater is a direct contact type which operates at 5 bar. So this is the feed water heater that we have. So this pressure is told to be at 5 bar. So P2 is given as 5 bar. Just write it so it will be easy for those who refer to this later. So P2 is basically the exhaust of turbine, and these are the inlet of turbine. Do we know anything else other than this? This is the only information that is given. So let's say if I ask you to plot it on, let's say PS plot, so would you be able to do it? So maybe I'll wait for a couple of minutes. So try to draw this, like represent this entire process on a TS plot. This is my entropy. This is my temperature. So you'll have the curve. Little tilt, something like this. So this is the vapor dome. So what are the different states? So the turbine outlet will be in the superheated state. So from the superheated state, you'll come somewhere here. And from here inside the condenser, what will happen is you just go till the saturated liquid state. And from the saturated liquid state, you have a pump where heat is getting added. So you'll go like this is a pump process, isentropic process. So after the isentropic process, there is a heat addition. So if you see here, after the isentropic process, the pump is isentropic process, there's a heat addition in the heater. So that heat addition will be along a constant pressure line. So let's say this is my constant pressure line till you reach another saturated liquid state. Once you reach the saturated liquid, you have the second pump that is operating. The second pump is again an isentropic process. And then again, you will have the same thing. So you'll have a constant pressure process to reach till here. And inside the boiler, again, you'll have constant pressure process. Inside the dome, it will be a straight line, and outside the dome, it will connect till this point. So there are two other constant pressure processes. So heat transfer is happening between the outlet of the turbine and this one. So that is happening along the constant pressure line here. So if I want to label my states, this is the turbine inlet. So state 1. This is the part of the turbine that is going into the feed water heater. So this is state 2. And this is the part where it is entering the condenser. So this is state 3. I should use a different line for the processes in this. So maybe let's put this line in a different color. Maybe use different kind of thing. Let's represent the dome with the dotted line. And these are the original processes. Or maybe let me put some directions so it will be easy for you. Okay, fine. I think you can understand from 1 to 2, 2 and 3. And then from 2, 3, after the condenser, it goes to state 4. From state 4, it is again the pump. So the pump is state 5. Again, it will go into the output of the feed water. So that is state 6. And finally, this is the inlet to your boiler, state 7. Now you can put the arrows as well. So you go from 1 to 2. This is the feed water heater where it will go. And this is the condenser. This is pump 1, this is pump 2, and this entire from 7 to 1 is the boiler process. So the boiler process is happening at a pressure of 30 bar. So that is inlet of your turbine. This is 30 bar line. And the exhaust is happening at a pressure of 0.1 bar. So this is 0.1 bar. And then there is an intermediate feed water one. The feed water is happening at 5 bar. That is also given. So this pressure will be 5 bar. We put everything here so it will be consistent. 30 bar, 5 bar and 0.1 bar. Okay, up until here, are there any queries? Okay, I guess there are no queries. So now with these properties, so what is happening? Let's say 1 kilogram of fluid is coming from the outlet of the turbine. So out of this, only a portion of it will actually go as an output into the condenser, and the remaining portion will go into the feed water heater. Let's say mkg of fluid is going into the heater, which means whatever is what the inside the condenser, what will you have? You will have 1 minus mkg. If 1 kg is the outlet of the turbine, out of that m is going into the feed water heater, and the remaining 1 minus m will go into the condenser. So this is very straightforward. So which means when both of these gets mixed inside your heater, and then it will go into the boiler. So inside the boiler, what will happen is you will again have mkg of your steam. So this m is something that we have to find that we do not know as of now, which we will do in the which we'll do now. Now we have a flow chart, and now we also have the TS plot. Yeah, of course, you can also do the same thing on a PV plot, but I'm not doing that here because once you understand the TS plot, it's the same thing, just that these things will be reversed. So so which of these will be straight lines? So this thing will be a straight line. This is a constant pressure heat addition in the boiler, heater, and all these lines from 5 to 2, like 2 to 5, 2 to 6, 5 to 6, 7 to 1. All these things will be straight line in the PV plot, and then the isentropic processes, that is the turbine process, and these pump processes 4 to 5, 6 to 7, and 1 to 3, all these things will be the slope lines representing the isentropic process. Other than that, there is nothing. So I'm not spending much time on that. So now what we need to do is the first question asks you to find the efficiency and steam rate. Efficiency, you need to know the enthalpy. Like efficiency is work by heat. So in order to calculate work and heat, you need to know the enthalpies. So let us write down the properties from steam tables. So first thing is we have at 30 bar and 400 Celsius. So let's say at state 1. So what we have, if you directly take from the tables, so you have H1 as 3230.9 kilojoule per kg. And what all things we need, again, it's the same process that we will be repeating again and again. So first we will calculate H1, this state will be known. For calculating properties at state 2 and state 3, all we need to do is, this is an isentropic process. So you'll calculate the entropy here, and you'll equate that with the entropy at 5 bar pressure, 5 bar pressure, and then calculate the enthalpy. So which means I need to know the entropy at 0.1, that is S1. If you look up the table, so it is in the superheated one, so it will be 6.921 kilojoule per kg Kelvin. So with these properties, what we do now, we know other equations. So let's say I want to find state 2. How do I calculate H? I don't know H, but I know one thing for sure, that this is an isentropic process. So S2 should be equal to S1. And from there, how do I calculate it? H2 and S1? So since we do not know whether, like I'm showing in the plot here as if 2 is in the superheated region, but then let's say we do not know it. Like we do not know whether this one is actually here, and so that this 2 can actually be inside the 2, which you do not know. So how do you calculate that? All you need to do is calculate the entropy of the vapor phase here. So that is Sg, and see if S2 is greater than Sg or not. If it is greater, then you will be in the superheated state. Otherwise, it will be inside the dome. So all we need to do is at 5 bar pressure, we have Sg greater than S2. So we are in the superheated station. Once we know we are in the superheated region, all we need to do is just take the table properties at the superheated region. So what is the temperature and pressure? The temperature will be if you take the temperature, that comes out to be around 172. Celsius, and that particular temperature H2 is. So how did I get this temperature? So I know the pressure, I know the enthalpy, sorry, entropy. So all you have to do is, let's say you have opened the steam tables, you go into the superheated steam tables. So these are the superheated steam tables. The entropy value that I have is 6.921 at 5 bar pressure. If you look up the 5 bar pressure, so this is the 5 bar pressure case. So the saturated vapor entropy 6.8212. 6.921 is greater than 6.8212. Maybe let me write here. So you're in the superheated region. That first part is clear. Now we'll go into the superheated steam table. So these are the superheated steam tables. All I have to look for is an entropy value that is 6.921 at a pressure of 5 bar. So we'll look up the 5 bar table. So this is the 5 bar table. Now if you see the entropy values, so it will be somewhere between 6.8213 and 6.9656. So all you have to do is interpolate between the saturated temperature and 180 degrees Celsius. The saturated temperature is 151. So the temperature will be somewhere between 151 and 180. So if you do the linear weightage, so these are the properties I got. I got the temperature to be around 172 Celsius. And similarly, once you get temperature, you can also calculate the enthalpy. So the enthalpy is coming out to be around 2796 kilojoule per kg. Sorry, I think that. So once I have, this is at state 2. Now similarly, I can calculate at state 3 also. At state 3, what do we know? All we know is S3 equal to S1. Now we also know the pressure. So at the rate 0.1 bar pressure, we will calculate, from the steam tables, we can get all the values. So SF is coming out to be around 0.649. And yeah, 0.6493, and saturated vapor is 8.1502. So you have SF and SC, and if you see here, S3 is less than SC. So the state lies inside the dome. So now we know it lies inside the dome. All we need to do is calculate the vapor fraction. How do I calculate the vapor fraction? All I have to do is make S3 equals to SF plus your vapor fraction times SC minus SF. So your X will be equal to, your vapor fraction is S3 minus SF by SC minus SF. So S3 equals to S1, that is 6.921 minus SF is 0.649 divided by SG 8.1502 minus 0.649. That is coming to around 0.836. Now I have my vapor fraction. Now, like once you have the vapor fraction, you can calculate HF, Hg, and then from there you can calculate the enthalpy. So that is straightforward. So H3 is HF plus your vapor fraction times, I'll directly write HFG means you will directly get that from the steam tables. So H3 is 191.8 plus the vapor fraction, sorry, I think there is a wrong unit, 0.836 times. HFG is 2390.8. That is coming to around 2192.2. Let's round it off. Kilojoule per kg. So now I have H2. So I know what is H1, I know what is H2, I know what is H3. So now if you are neglecting the pump work, like it is mentioned in the problem that you can neglect the pump work. So if you are neglecting the pump work, so HF is equal to H5 and H6 equals to H7. So all I can say is H4 is approximately equal to H5 and H4 you already know. H4 is at 0.1 bar, whatever is the saturated liquid state. So that is this HF, so that is 191.8. And similarly, we can also do the same thing here. So H6 will be equal to H7. And at 5 bar, that is around 640.1. Why am I calculating all these things? Is just because I need to determine what is my steam rate. Like that's the first part of the question, efficiency and the steam rate. So in order to determine the steam rate, all I will be doing is applying energy balance here. So that is m times whatever is the change in enthalpy, like whatever is incoming is outlet, whatever is this 1 minus m times h5 that is coming from the pump plus the m times whatever h2 that is coming from the turbine should be equal to the total whatever is leaving. The leaving is the inlet of my pump. So if I apply energy balance across the heater, so all we have is whatever is coming in should be equal to whatever is going out. So m times what is coming in is, so if you see this thing, so this is where your heat transfer is happening. So what is coming in? So this is one incoming fluid, this is another incoming fluid, and this is the outgoing fluid. So you can also see the same thing here. So we are neglecting the pump works. So whatever is coming from the turbine from 2 to this thing, if the pump work is neglected, should be equal to whatever is this thing. Because this is neglected, so this should be equal to this. What we have then, m times h2 minus h6 should be equal to 1 minus m times the other one. 1 minus m is from the other one. So that is 6 minus 5. Since the work is neglected, 5 will be equal to 4. So that will be 6 minus 4. So you can solve this equation. So H2 is already known, 2796 minus H6 is also known, 640.1 should be equal to 1 minus m. H6 is already known, minus H4 is also known. So if you solve that, you will get m equal to around 0.172. So what does this mean? So for every kilogram of output that is coming from the turbine, or for every kilogram of input to the turbine, you're you are sending around 0.172 kilograms of it into the feed water heater and the remaining into the condenser. That is the mass fraction that is getting transferred. Now we know the mass transfer, so we can directly calculate the work done. So this is the steam rate. So this is the first part of the problem. The next part is calculating the work done in heat transfer rate. That is again straightforward. So how do I calculate the work done by the turbine part? This we have done even before. So the net work done by the turbine is inlet minus outlet. So what is my, so this is my turbine. This is where the expansion process is happening. So it is moving from, like, the mass of 1 kilogram is moving from state 1 to state 2. So it will be 1 times H1 minus H2. And then this is going into the heater from which I cannot extract any work. So this should not be added into the work done. But the state from 2 to 3 is around mass of 1 minus m kilograms. And but this is where we are extracting work again. So that also should be added into your work calculation. So that will be 1 minus m times H2 minus H3. So this is 1 times, I put 1 times H1 minus H2 plus 1 minus m times H2 minus H3. So if I substitute the values, H1 3230.9 minus H2 is 2796 plus 1 minus m times H2 minus H3. H2 is again 2796 minus H3 is 2192.2. This comes out to be around 934.8 kilojoule per kg. Now this is the turbine work. Now what is the heat input to the boiler? I'll just call Q input. So if you see again this process, so where is the heat getting added? The heat is getting added in this process. So from state 7, which is outlet of your inlet to your boiler, to state 1. So this is where heat addition is happening. So I need to do H1 minus H7, but we are saying that the pump work is neglected. So H7 is almost equal to H6. So you can directly do H1 minus H6 to get your heat input. So that will be 1 times H1 minus H6. H1 is 3230.9 minus H6 is 640.1. That is coming to around 2590.8. So now how do I calculate efficiency? Efficiency is again straightforward. The efficiency is basically your, this is the first part of the question. So efficiency will be your whatever is your work done divided by whatever is your heat input, output by input. Work done is 934.8 divided by 2590.8. That is coming to around 0.3608. So it is around 36% efficiency. Now what is the steam rate? Steam rate is basically, you have seen before. Look, so we have a work done of around 934.8 kilojoule per kg. So if I need around 1 kilowatt hour, so how much should be what should be my steam rate? What should be the rate at which I need to supply my steam? So if I want it in kilowatt hour, so for example, how do I put it? So 1 kg of steam gives 934.8 kilojoule of work. So 1 kgr of steam rate gives 4.8. I can convert this into kilowatt. So 1 kg per hour of steam, if you convert it into kilowatts, so it will be 934.8 by 3600. Now the question is, for 1 kilowatt of work, what should be the steam? What should be the rate of steam? So for 1 kilowatt of work, steam rate will be inverse of it. So that is 3600 by 934.8. That will be 3.85 kilogram per kilowatt hour production of work. This is clear. So I don't think there are any questions. So efficiency we can calculate and steam rate we can calculate. So the next part of the question asks you to find the increase in the mean temperature of heat addition, efficiency, and the steam rate as compared to the Rankine cycle. So the same thing without regeneration. So if you do not have regeneration, what would happen? So let's say first we'll calculate the mean temperature. Let's do for this particular case with regeneration. What is the mean temperature? So how do you define mean temperature? Mean temperature is where your net heat addition is happening. So your net heat addition is H1 minus H7. And how do I find the mean temperature? We use a relation that we already know, del Q is TDS. So with regeneration, let me call it Tm1. So what will be the value of Tm1? Just as I said, so it will be the net heat addition that you are doing. So which is H1 minus H7, that is approximately equal to H6 in this particular problem, divided by what is your net entropy change. Net entropy change is S1 minus. So what would be the net entropy change? So this is almost equal to this is almost equal to this. So you can approximate this particular point to be equal to the point over here. So it will be S1 equal to S3 and this equals to this. So I can write S1 minus S7, or maybe I'll write S1 minus S7, and this I can approximate with the whatever values that we already have. So that is H1 minus, then a heat addition is happening. So if we neglect all the pump works, so what would happen if we neglect the pump works? 7 will be equal to 6, 6 will be equal to 5, 5 will be equal to 4. So I'll just write directly as H4 divided by your S1 minus S4. I already have all these property values, so I can directly substitute them. H1 is 3230.9 minus H4 is 191.8 divided by 6.921 minus 1. That is coming to around 424.5 Kelvin, which is my, if you do minus 2, that is around 201.5 Celsius. So this is clear. Okay, are there any questions in this? So basically what is mean temperature of heat addition is a net change in your enthalpy. So that is between state 4 to state 1 divided by the net change in the entropy. So delta H is approximately your delta H is your delta Q. So delta Q divided by the change in entropy should give you the mean temperature of heat addition. So all we are saying is if it were a Carnot process, this would be the mean temperature of heat addition. This is clear. Now let's say what would happen if, for suppose, because of regeneration, what is happening? Sorry. So whatever we have done here is we'll compare this with this. So this versus this is okay. So H1 minus H7 is your heat addition divided by your S1 minus S7. Let me just do that again. So let's do one by one. With regeneration, is H1 minus H7 by S1 minus S7. So that should give you H1 is 3230.9 minus H7 640.1 divided by S1 6.91 minus S7 is 1.8604. If you do this, that comes out to be around 511.9. Converting to Celsius. Yeah, this is with regeneration. So if you did not have this regeneration, what would happen is you will directly grow from 4. So if you do not have this regeneration, the output of your pump will be equal to your boiler. So this will be 1, this will be 2. So eventually you will be like from here, you will be directly go to the inlet of your boiler. So without regeneration, let's say 2 will be H1 minus H4 divided by S1 minus S4, which we have calculated just now. Hi, good evening. Hello. Good evening. Do you have some queries or do you want me to continue with the problem that I'm going? Do you have some queries or doubts or something that you want to discuss, or can I continue with what the problem that I'm going on? Okay. So I'll just finish this problem and then we'll discuss your doubts. So you can also see the problem. You can go through the problem and then. So it's basically a regenerative cycle. So the outlet of your turbine will actually send into a heater, and then this is your feed water heater, and the outlet of this will again go into the pump. So you can see it in the process over here. So this is the turbine inlet from where it will go into a part of it will go into your heater, and the remaining part will go into your condenser. This is your condenser. This is pump 1, pump 2, and then state 1 it will go into the boiler. You are required to find the efficiency and whatever is this fraction of the total steam rate. And the same cycle you repeat it without regeneration. Let's say you do not have this regeneration. So basically remove this entire part. So this pump is connected to boiler. So what would happen in that case? You have to compare case 1 with case 2 and see what is the mean temperature of heat addition, efficiency and steam rate. So that was what we were trying to do before. So kind of solve the first part. So now we are like solving for the case when we do not have any regeneration. We do not have any heat regeneration, so that will be H1 minus. So if you do not have regeneration, this will be directly connected to your boiler. So it will directly go here. So it will be H1 minus H4 by S1 minus S4. We'll just substitute the values. S1 into 1 minus 0.64. We convert into Celsius, so that will be 219. Now you can see the difference between the mean temperature of heat addition in case 1 and case 2. So when you have regeneration, your mean temperature for heat addition has increased. So what would happen to efficiency? We go, the first part asks you about the mean temperature of heat addition. Now we talk about efficiency. Now for efficiency, we need to calculate the turbine work done, and we also need to calculate the heat addition in the boiler, and then divide them and see what is happening to the efficiency. So the turbine work done, let's say without regeneration, if you see the states, if you do not have this regeneration, turbine work will be state 1 minus state 3, H1 minus H3 times your mass flow rate. So this is straightforward, H1 minus H3. H1 I already know, 3230.9 minus H3 we have calculated before, 2192.2. That is coming to around 1038.7. So once I have the work done, I can calculate the steam rate. Steam rate, as we have defined before, it is the amount of steam that you have to send so that you will have 1 kilowatt hour of work done. So if you convert it, so kilowatt hour, so that is 3600 seconds divided by the amount of work you are doing. That comes out to around 3.46 kilogram per kilowatt hour. Now the efficiency case. So how do you calculate efficiency? Is the net work done, or I'll write in terms of enthalpy. So the work done is H1 minus H3 divided by the heat addition. Heat addition, if there was no regeneration, state 4 would be where your heat is getting added, like after neglecting the pump work. So it will be H1 minus H4. H1 minus H3 we have calculated before. 3230.9 minus H3 is 2192.2. H4 191.8. That is coming to around 0.3418. So if you see the efficiency, is this is without regeneration, you have around 34% efficiency, and with regeneration we got efficiency around 36%. So the efficiency has increased. Your mean temperature of heat addition also got increased, and the net work done, if you see the net work done previously, with regeneration it is 934, without regeneration is 1038. So even though the net work done by the turbine has decreased, but because your heat addition, like both the turbine work done as well as the amount of heat you added in the boiler, both got reduced. Because your heat addition is being done at a very higher temperature, the efficiency of the overall system is increased. Are there any, I don't think there are any queries in this. So yeah, you have some query, right? So we'll discuss that and then we'll move on to the next problem. Okay, 3 to 4. Okay, let's say this one. Which one? This one. Okay, you don't have without regeneration. So this is your 1, this is your 2, this is your 3, and this is your 4. So from, you're speaking of TS plot only, right? Yeah, okay. So 3 to 4 is your from the pump. Maybe I should, maybe I have a picture before. This is TS. Okay. So 3 to 4 is this one you are referring to. Okay. Hello. Yeah. Superheating is here, right? Yeah. Oh, if there is no superheating, it will end here. Okay. Hmm. 4 to 5 is, this is the entry point of your boiler, right? This is the 3 to 4 is your pump. So after coming from the pump, you will be in the subcool stage. So this is the constant pressure line. So inside the boiler, you are adding heat at constant pressure. So from 4 to 1 is entire one process. That is your constant pressure heat addition process. So this line you are referring to from 4 to 5 is the constant pressure line. So now you are adding heat, so its temperature increases along the constant pressure line. Yeah. So what so that's okay, that doesn't answer your question. So what was your question? That is because inside the dome your pressure remains constant and temperature also remains constant. So like inside the dome, when this evaporation is happening, your temperature is practically constant. So your pressure also doesn't change there. Yes. 4 to 1. The entire thing is one process. 4 to 5, 5 to 1. Yeah, that is this entire thing. This entire thing is a constant pressure line. Yes. That is also the same. That is also heat is being added at constant pressure. So you are in the subcool stage, you will add a heat, so it will come into liquid state. Now, once it comes to liquid state, when you are adding heat, the temperature does not change. Like above, like during the phase change, temperature remains constant, right? This is that portion where your temperature is constant. And once it becomes vapor, if you add further more heat, the temperature will keep on increasing. So this there you comes another line. Okay. Hmm. Hmm. So if you see the Brayton cycle, like there, the whatever is in, maybe I'll just draw it. Or maybe I'll take a reference that is already available. Okay, or let me put it in this way. So what you mean by cycle is because whatever is the end state, again, like whatever is the fluid that is coming here, if you consider the Rankine cycle, whatever is the output of your boiler, turbine, everything is the same liquid. It's a closed loop fluid, right? It's the same fluid. Whatever is output is actually going as again as input wherever you break the cycle. But what happens in Brayton cycle is you are taking air from outside and then some combustion happens because of which heat is added. And then these exhaust gases are expelled out into the atmosphere, right? You're not taking back the exhaust gases again and then you're sending in them back. But understood? Okay. Yes. Yes. So the last thing, the exhaust gases to fresh air is not really happening inside, but you are representing that in your cycle. I mean, when you draw the Brayton cycle, then you're representing that in your figure, but that is not actually happening. Okay, I didn't solve a Brayton problem. Okay, I'll put that. Okay. In the okay, you are now talking of vapor compression cycle. Okay. Yeah, yeah, depending on your temperature and pressure, right? Brayton is a gas cycle, right? It's air, it's just gas. So at the temperatures and pressures at which you are operating, it is completely in vapor phase. I mean, it is gaseous phase. You don't have two phase thing. It depending on the pressure and temperature, right? Yeah. The R134A, the ones that we are operating, it will be in two phase also. So you'll have the, inside the evaporator, it will be two phase. Inside the condenser, it will be two phase. Hmm. You can draw PV diagram for Rankine, right? I just wrote IL, but you can draw PV diagram. What's wrong with that? Yeah, sure. It will take a little of time. I just don't want to write the notes again, so I can put it in a nice format. So instead of hand drawing it, put it in this. So if you were to represent the processes on the okay, first let's move to the line. So now say this is your boiler. Like you are going from the saturated liquid state to superheated state. So this is your constant pressure process, constant pressure heat addition process. This is your turbine inlet. So from turbine inlet to turbine outlet, you should be following the isentropic process. So the entropy line there will be something like this. You will enter your inside the dome region. Now this is the condenser. So inside the condenser again you will go till your whatever subcool state you want to go to, and from here again it will follow the isentropic process. Let's say you go somewhere here. Let's say this is your subcool process. So this is that extra thing that you told that from 4 to 5 we were speaking of before, right? So this curve will be actually little. I can't adjust this here, but depending, this is an isentropic process line. This and this are isentropic processes. This is your constant maybe output number. So this is your turbine inlet. This is condenser inlet. This is the pump inlet. This is that 4 and this is that 5. So 4 to 5 is a constant pressure heat addition from subcooled liquid to saturated liquid. 5 to 1 is another constant pressure heat addition. So till you reach your saturated vapor, sorry, superheated state or saturated vapor state, whichever, wherever you end it. Okay. Yeah. I have a couple of other problems also. If you want, you can try solve them, or I'll upload them so you can solve it later, depending on your convenience. Okay, fine. So here we have a simple vapor compression cycle that is producing 5 tons of refrigeration. The enthalpy values are directly given to you. The inlet to the compressor, exit of the compressor, and exit of the condenser are already given. You need to estimate the refrigerant flow rate. Like you know the load. So from the load you equate to that m dot times delta H, from which you can get the refrigerant flow rate. And then COP is your whatever is your output by input. The output is this is the requirement divided by whatever you use of compressor work. You know the enthalpy of the inlet and outlet to compressor, so from which you can calculate the compressor enthalpy. Sorry, compressor work done. So you'll get the COP. Power required to drive the compressor is the output, like this output divided by COP, and the rate of heat rejection to the condenser. If you apply the entire cycle balance, you'll be able to calculate this one. So let's solve this problem. So how do I calculate? So how do I calculate these properties? So first, let's write down the information that is already given to us. The total heat load is given as 5 tons. So 5 tons, if you convert it into kilowatt, so that will be 5 into 1 ton is 14,000. So that will give me around 70,000 kilojoule per hour. So if I convert that into per second, so 70,000 by 3,600, so that will give me around 175 by 9 is 19.44 kilowatt, or let's use the same thing, kilojoule per second. Like for work we are using kilowatt, so for heat we'll use kilojoule per second. So that is the heat load. Now we have the heat load. Now let us write the properties that are given to us. So from our regular notation, H1 is your so H1 to 2 is my evaporator. So I'll just write the processes. So 1 to 2 is, sorry, 1 to 2 is evaporator, and then let's 2 to 3 is after the evaporator it goes into your compressor, and 3 to 4 from the compressor it will go into your condenser where it loses heat, and finally 4 to 1 is where your throttling happens. After throttling it will eventually come back to your original phase, like it will start from the evaporator and then this keeps happening. So So what is input? So here what is given to us? The enthalpy values at the inlet to the compressor. The compressor inlet is 2. So state 2 is given as 183.19. And the enthalpy at the exit of the compressor, that is H3, is also given 209.41 kilojoule per kg. H2 and H3 are given. And it also told that the exit of the condenser. So the exit of your compressor is the inlet of your condenser. So 3 is 3, and the exit of the condenser is state 4. So state 4 is given as 74.59. Now for the throttling process, we know H4 equal to H1. So, and what is H1? That is H4 is 74.59. So now we have the enthalpies for all the 4 states that we need. So 1, 2, 3, 4, all the 4 state enthalpies are there. Now let us calculate one by one. So the first one asks you to find the refrigerant flow rate. So let's equate the net heat load on the load happens on the evaporator. Refrigeration load acts on the evaporator. So the evaporator process is process 1 to 2. So if I do m dot times the H2 minus H1 is my heat load Q. So I need to calculate m dot. Q is 19.44 divided by H2 minus H1. H2 is 183.19 minus H1 is 74.59. That's around 0.179. We have m dot is calculated. The second we need to calculate the COP. So in order to calculate COP, we know it's basically refrigeration load divided by the work done. So let us calculate the power first. Work done for the compressor is whatever m dot we have calculated times the compressor inlet minus outlet, because your work is being done on it. So it will be outlet minus inlet. So that will be H3 minus H2. So m dot is 0.179 divided by 179 into H3 minus H2 is 183.19. It's around 4.693, 4.694. Now I know what is my work done. I know what is my refrigeration load. So COP is straightforward. COP is your output by input. The output is the refrigeration load that I want divided by the input is the work done that I am doing. So the refrigeration load is 19.44 divided by the work done is 4.69. That is coming to around 4.144. Let's remove all these decimals. It's around 4.144. COP is calculated. So the next one is the rate of heat rejection to the condenser. So for the condenser is the process 3 to 4. So Q rejected will be m dot times the condenser heat is getting rejected, so enthalpy gets reduced. So it will be inlet minus outlet. So H3 minus H4. M dot is 0.179 times H3 is 209.41 minus H4 is 74.59. Around 24.13. So that is it, we have calculated. So this is a very fairly straightforward problem. Like since we haven't discussed any problem on this year, I just put this small problem so that you'll be familiar with this methodology. Now let's take a little bit bigger problem. So we have a food storage locker. We have a food storage locker that requires a refrigeration system of 2400 kilojoule per minute. So this is my refrigeration load. Capacity at an evaporator temperature. So the evaporator temperature is given as 263 Kelvin and a condenser temperature of 300 Kelvin. The refrigerant used is freon 12. The properties are given here and is subcooled by 6 degrees Celsius before entering the expansion valve. So the throttling, the output of after the condenser output, it is again subcooled till it reaches the subcooled temperature is given as 6 Celsius. So from the saturated temperature, this will be less than 6 Celsius and before entering the expansion valve. and the vapor is superheated by 7 degrees Celsius before leaving the evaporator. The compression of the refrigerant is a reversible adiabatic process. So you can assume it to be so reversible adiabatic is basically your isentropic process. And the refrigeration compressor is a 2-cylinder single acting with a stroke equal to 1.25 times the bore. Bore is basically the diameter. Stroke is the length at which the piston moves, and it operates at 1000 rpm. So from this information is given so that you can calculate the work done. Take the liquid specific heat to be 1.235 kJ per kg Kelvin, vapor specific to be 0.733 kJ per kg Kelvin. You need to calculate the refrigerating effect per kilogram of mass of the refrigerant to be circulated per minute, theoretical piston displacement per minute, theoretical power required to compress in kilowatt, heat removed through the condenser per minute, and theoretical bore and stroke of the compressor. So it's a bit of involved than what we have discussed previously. So let's see one by one. So how will this process look? So let's say I want to plot it on a TS plot. So I'm not drawing the dome again. So like we don't want to waste time on drawing the dome. So what are the processes we are having? So let's say this is state one. We are starting here. So first process is inside the evaporator. So you'll start from here and then you'll go somewhere. And what happens after that? You are set that the temperature, you are entering the superheated steam region. So maybe I should draw it down so it will actually be the more clear. So let's say the dome goes something like this. It goes way higher. So similarly, you have other portion here, something like this. So initial stage is like after throttling, you will be somewhere here, somewhere in the two-phase region, and then you will go till the saturated liquid. And once you reach the saturated vapor, it says that you are superheating by certain amount of temperature. So, so this is the first process inside the evaporator. And then you have some superheating because of okay, now the question, so how is superheating done? So is what process should I assume for superheating? Again, whenever you're heating, you're assuming it to be a constant pressure process. So you undergo a constant pressure process till the new state, and once you reach that, you will have compressor. The compressor is an isentropic process, so your temperature will increase to a certain point. And once you reach that, then it will be the condenser. Condenser will again be a constant pressure process. So you'll come till the saturated vapor phase, and from the saturated vapor phase, you'll go again till the saturated liquid phase. And it again, it's told that before it is going into the throttle valve or expansion valve, subcooling is done. So the subcooling is done so that your temperature will decrease, and this temperature decrease happens along a constant pressure line. So again, this temperature drops by a certain amount, so you'll move to a new point. And from there is where your expansion process happens. This is your expansion process. So again, since it's a reversible process, I use dashed line. And of course, this won't be a straight line. So it will be a little bit. Okay, so this is clear. So the inlet is, sorry, this is my evaporator inlet. This is my ideal evaporator outlet. But then because of the superheating, there will be the original state is 2. So I'm representing the previous state with 2 prime. So this is the compressor output is state 3, and this we don't need. Let's call this 3 prime. From 3 prime, you'll go to state 4. And this is like in the saturated phase, this will actually be very close to your dome. It will actually follow very close to this one. So maybe I'll just draw this very close to this. So are there any questions in this up until this part? If there are no questions still here, then it will be pretty straightforward from here. So let us calculate the properties one by one. So let's say I want to calculate H2. H2 is in the superheated state. So how do I calculate the properties H2? So I'll start with H2 prime. H2 prime I can get because this is the saturated vapor phase, so I'll get H2 prime. Plus inside this one you can assume it to be Cp delta T. And Cp is already given in the problem. Cp times delta T. Delta T is your T2 minus T2 prime. And all the values are given here. So evaporator temperature is 263 Kelvin. At 263 Kelvin, enthalpy of vapor is 183.2, and the vapor. So let's substitute the values. So H2 prime is 183.2 plus Cp is for the vapor is 0.733 times T2 minus T3. T2 minus T3 is the extra amount of superheat that is given is 7 degrees Celsius. It's already given in the problem. This comes out around 188.33. Okay. Now we have H2. Similarly, you can like the next process is to need to find the H3, for which we need to know S2, because S3 equal to S3 is S2, then we can calculate enthalpy here because we know the pressure here. So now I need to calculate S2. So how do I calculate S2? This we have done a lot of times. So S2 is again, you know the process from this one. This is a constant pressure heat addition process. So it will be S2 prime plus, for a constant pressure process, it will be Cp times ln T2 by T1. T2 by, in this case, it will be T2 by T2 prime. So if you substitute the values, S2 prime is the entropy of vapor 0.7020 plus Cp is 0.733 times known T2 by T2 prime. So what is T2 and what is T2 prime? So T2 is already known here. The saturated temperature is 263 plus degree of superheat is 7 divided by the actual temperature is 263. That's around 0.7212. Okay, let's remove all these decimals. We have S2. So now we know that inside the compressor S3 equal to S2. I don't have to specify that. But I don't know what is the temperature at point 3. Like, why would I require the temperature? Like, all I need to know is determine the temperature, and basically I need the enthalpy here. So I know the pressure of this one. Do I know the pressure of this one? The pressure of this one will be 7.45 bar. So you can directly look up the table for 7.45 bar and a pressure of and an entropy of 0.7212. So look up superheated tables to find the enthalpy. But the problem is, let's say you do not have the table. All the information that is given to you is just this information is given. So how do I do? I back calculate it. So I know the He value here. So all I would be doing is H3 is H3 prime plus Cp times T3 minus T3 prime. This is clear. So do I know T3 prime is something that I know. T3 prime is this temperature, 303 Kelvin. But I don't know T3 value. So how do I calculate T3 value? Again, we will follow the same logic that we were following. So we know S3 prime, S3 prime is the value of the entropy, saturated vapor entropy. So that is 0.68, this is entropy vapor, 0.6854. So all we do is, the process is a constant pressure feed iteration. S3 will be S3 prime plus Cp ln T3 by T3 prime. So you already know the value of S3, that is 0.7212, should be equal to 0.6854 plus Cp is 0.733 times ln T3 is unknown divided by T3 prime is 303. So if you solve this equation, you can get the value of T3. That comes out to be around 308 Kelvin. Once I know the value of T3, now I can calculate my enthalpy using this equation here. So H3 will be H3 prime. H3 prime is enthalpy of the vapor 199.6 plus Cp times 318 minus 303. That is 210.6. So now I have H2 and H3. Now again, this is straightforward. H4 prime will be equal to H1, and which we already know H4 is approximately equal to H4 prime, so that will be 64.6 minus. So let's calculate. So H4 is known. How do I calculate other one? So H4 is the value of this saturated liquid. That is 64.6. So if I want to calculate H4 prime, that will be H4 minus Cp H4 plus Cp times T4 prime minus T4. So this is again straightforward. So H4 prime will be H4 is 64.6. Since it is subcool and the liquid enthalpy specific is given as 1.235. 1.235 times 6, that it comes to around 57.19. Now I have H4 prime. So in throttling, the enthalpy remains constant. So H1 will be equal to H4 prime, that is 57.19. So this is always a significant step in any of your problems. The first thing is determining the states, the properties at each and every state. This is the first thing that you're doing in any of these problems. Once that is done, most of the problem is solved. Now let us do a few more things. The first question asks you to find the refrigerating effect per kilogram of the fluid. So refrigerating effect is where does the refrigerating effect happens? It happens inside your evaporator. So as the refrigerant evaporates from state 1 to state 2 is where you are getting the refrigerating effect. So this is straightforward. That is H2 minus H1. I have already written down the values of H2 and H1. H2 is 188.33 minus H1 is 57.19. That is 131.14 kilojoule per kg. So this is straightforward. Now the next question is mass of the refrigerant to be circulated per minute. What is my required heat load? The heat load is 2400 kilojoule per minute. So mass of refrigerant to meet 2400 kilojoule per minute load will be simple. So you have to divide this 2400 divided by per kilogram you have 131.14. So that gives me 18.3 kilogram per minute. So this is straightforward. Now what is the piston displacement per minute? So basically, what should be the velocity of your piston? So this, how do you calculate? Is basically whatever is your. So all we have to do is in order to meet your required. This is a displacement, positive displacement pump, or your compressor is a positive displacement machine. So the volume flow rate will be equal to your net displacement. So that is the area times your velocity times your density should give your mass flow rate. So mass flow rate I already know, that should be 18.3 kilogram per minute. All I need to know is piston displacement minute is basically your volumetric flow rate. So this is your volumetric flow rate, and that you can get directly by m dot divided by density, or you can multiply with specific volume, whichever one you prefer. And which specific volume? This should be the specific volume of your compressor, so that will be the compressor inlet, so that is at state 2. How do I calculate the value at state 2? So again, I know the specific volume at the specific volume of vapor is given as 0.0767. So V2 prime is given as 0.0767. I need to calculate V2. So which process is happening here? 2 prime to 2. It's a constant pressure heat addition process. So in a constant pressure heat addition process, what will happen? Your pressure is constant, so V will be proportional to T. So we can use the relation V2 by T2 is equal to V2 prime by T2 prime. So from this we can directly calculate V2 is V2 prime 0.0767 times T2, which we have calculated before. T2 is 263 plus 7 divided by 263. 263 plus 7 divided by 263. That comes to around 0.07874 meter cube per kg. So the question is to calculate the volumetric flow rate. This m dot, which we already calculated before, 18.3 times 0.07874 comes to around 1.241 meter cube per minute. So the flow rate is calculated. What is the theoretical power required to run the compressor? That is the next part of the question. Power required to run the compressor. So why are we calling theoretical? Because we are neglecting so many losses that can happen because of the inefficiencies present inside the compressor. So maybe I'll just put theoretical power of compressor. It's again simple. We have already calculated the mass flow rate, and we know H2 minus H1. So all we have to do is multiply that. So m dot times H2 minus H1. So m dot is 18.3 times H2 minus H1 is 121.14. So that will give me, okay, let's convert it into kilowatt. So I'm dividing with 60. That is around 6.7 kilowatt. This is straightforward. The next part of the question asks you to find the heat removed through the condenser per minute. So how do you calculate heat ejection? Heat ejection is this one. So that is basically H3 minus H4 prime. I know all the state properties. So this is again straightforward. Heat removed through condenser will be m dot times H3 minus H4 prime. I know m dot. Let's convert everything back. H3 is 210.6 minus H4 prime. 4 prime is 57.18. That comes out to around 2807. 0.4 kilojoule per minute. And the last part asks you to find what is the theoretical bore and stroke of the compressor. Bore is the diameter and stroke is the length in which the piston moves during one cycle. So, like during part of the cycle. So, how do we do that? First, let's say theoretical piston displacement. That how many do we have here? So it says that you have the refrigeration compressor is a two-cylinder, which means there are two cylinders. So all you have to do is the per cylinder is how much theoretical piston displacement per cylinder is straightforward. So since you have two cylinders, all you have to do is divide it into two of them, which we have already calculated before. The volumetric flow rate is 1.441 divided by two cylinders. That is 0.7205 meter cube per minute. Now the next question is the length of stroke. How there again another relationship is given that the stroke is equal to 1.25 times the bore. So given stroke is L is 1.25 times the diameter. So what can we make from there is the volumetric flow rate is given as 0.7205 is a volumetric flow rate, that will be pi d square by 4 times the length times whatever is your RPM. I'll just use N for the RPM. So this is the total volume that is available inside the piston. That now when the piston moves, this entire volume of liquid will go out. So this pi d square by L times how many times you are doing, how many rotations you are happening, that many times this will be moving off. So again, that depends on the stroke of it. So since here it says single acting, so I'm just doing that. If I substitute the values, we know the values as N is 1000 RPM. Solving the above two equations, you can get your L and D. So if I solve, I'm getting D equal to around 0.09. You can check and confirm me. And L, I'm getting around 1.25 times 0.09 is 0.1125. Just check and let me know if you're getting the same answers. Yeah, I guess you got the same answer. So we move on to the last problem. So you can go through the problem. Okay, I hope you have gone through that. So air is drawn to a gas turbine unit, 15 Celsius and 1.01 bar pressure. And the pressure ratio is basically inside the compressor. So this is the output to input ratio is 7:1. The compressor is driven by the high pressure turbine, and a low pressure turbine drives a separate power shaft. The isentropic efficiencies of the compressor and the high pressure and low pressure turbines are 0.82, 0.85, and 0.85 respectively. If the maximum cycle temperature is 16 Celsius, calculate the pressure temperature of gases. The net power developed per unit per kg of the gas that flows, the work ratio, thermal efficiency of the unit, and neglect the mass of the fuel and assume the following. The compression process, use Cp and gamma are given. Combustion and expansion process, again Cp and gamma are given. So what do I have here? So let us again draw the schematic first, and then we'll also see. So let's say if I want to draw it in a schematic, so what are the different processes I'm having? So I have a combustion chamber, or this is basically your boiler in case of your Rankine cycle. This is my combustion process. And the output of this will go into your compressor, where your pressure is increased. And from the compressor, there are two turbines. The first is a high pressure turbine. Let's say it is high pressure turbine. And the output of this will again be fed into a low pressure turbine. And from there, you have your generator. So from where your power is getting generated. So we'll remove the last part for now. So the output of this will be the exhaust. So this exhaust will again be fed back into the compressor. So this exhaust, again, it has to lose heat to the ambient, and then the fresh air will again come into your combustion chamber. So this will represent the last cycle. So if I just connect them with the appropriate arrows. So from the combustion, going to the compressor. From the compressor, you first go to the high pressure turbine. From the high pressure turbine, you go into the low pressure turbine. And from the low pressure turbine, it will be exhaust. Just write exhaust here. This is why it is not called a cyclic process. Okay. Now let's label. Okay, there is an inlet. So let's just label him so that you know the processes that I'll refer to again. Let's say we draw some ES diagram, and then we'll show this thing. So inlet is state 1, then it goes to the combustion chamber. So let's call this 2 prime, and then why I'm using 2 prime? Like, is this because all these processes are okay? Maybe I'll explain that in a little time. Once I draw TS diagram, then it will be a little clear. 4, and then let's call this 4 prime, and the exhaust again, let's call this 5 prime. This is the normal block diagram. Now let us draw this again on a TS plot, so it will be much better. So what are the different processes I have? So I'm having the entire process is happening at two different pressures. So in a Brayton cycle, that is what this compression ratio refers to. The first pressure, the lower pressure is 1.01 bar, and then there is a high pressure. The pressure ratio is 7:1. So the high pressure will be 7.07 bar. So First thing is we just draw the constant pressure lines. So this is one line. It will be a little bent. And similarly, you'll have for the other line as well. Yeah, of course, they won't be parallel to each other because your temperatures are different. This thing will actually be something like this. Okay. So now let's saw different processes. So ideally, you would undergo an isentropic process. So this is the first process. The compression process is isentropic, but then in real systems, we do not follow that. We'll follow some different process, because of which I'm denoting this with the total line, or we'll do the total lines later. First, let's draw an ideal Brayton cycle and then we'll explain it. So first thing is this isentropic compression process, and then you have a heat addition process that is happening at constant pressure. So let's say it come to this point, and again you'll have an isent. So we have an intermediate line as well. Let's draw the intermediate line as well. So this is the intermediate pressure. So we have three different pressures. So one is 7.07 bar, and then we have 1.01 bar pressure, and then there is this intermediate pressure. So how do I calculate the intermediate pressure? I'll leave that for now. There is an intermediate pressure that we will get to that a little later, but there is an intermediate pressure. So the first turbine, so if you see there is a high turbine, so 3, and then there will be intermediate pressure, and then this will be the final pressure. So we'll see how to calculate the intermediate pressure in a little bit time. So after your heat addition process, this is the first turbine process. Again, this is an isentropic process. Ideally, if it was an isentropic completely, then it would be something like this. But because we have the process is not isentropic, it will end at a different state. So from the different state, again, this is another isentropic process. So if everything were normal, so this would be my stage 1, this would be stage 2, this would be stage 3, 4, and 5. And again from 5 to 1 is the last process. But because none of these processes are reversible, we'll have the irreversibility, so entropy will be a little higher than what it is supposed to be. So this is the first deviation, and the same thing keeps happening everywhere, even in the expansion process. So this process is what we are representing with 4 prime. Because of this irreversibilities, all these process states will change. So this will be 2 prime, and this will be 5 prime. Are there any questions up until now? Okay, I guess there are no questions. So if there are no questions, now let's get started. So the first question asks you to find the pressure and temperature of gases entering the power turbine. So which one of these is a power generating turbine? So both, there are two turbines. The compressor is driven by the high power turbine, high pressure turbine, and the low pressure turbine drives a separate power shaft. So the power is from the low pressure turbine. So we need to determine, in order to get the power, we need to know what the states are, state 4 and 4 prime. That is our first step. So how do I do that? So let's calculate all the states, and then we'll use them one by one to calculate the work done. First thing is pressure and temperature of gases entering the power turbine. So if you consider the isentropic process, consider the process 1 to 2, that is isentropic. 2 prime is where your reversibility comes. So it is straightforward. 1 to 2 process is isentropic process. So you know T2 by T1 is in terms of pressure. Pressure ratio is something we already know. So we'll denote in terms of P2 by P1 power gamma minus 1 by gamma. So if you substitute the values, P2 by P1 is 7, T1 is already known. So if you substitute the values, this P2 by P1 is 7 to the power gamma minus 1 by gamma is 0.4 by 1.4. That comes to around 1.745. Now for T2 will be T1. T1 is given as 15 Celsius. T2 will be 1.745 times T1. That is 5.5 kilo. Now I know what is T2. Now how do I calculate T2 prime? That is where your compressor efficiency comes. So the efficiency of the compressor is given as 0.82, or in terms of our definition, efficiency will be whatever is it the ideal one. It was in the real scenario versus the isentropic scenario. So that will be in this case T2 minus T1. So this is what would happen in ideal case. Since it is compressor, it will be ideal by the actual, that is T2 prime minus T1. So eta compressor is 0.82. T2 we have calculated just now, 502.5 minus T1 we already know, divided by T2 prime is something that we are trying to calculate, minus T1. There is a mistake here. It will be T2 minus T1 divided by T2 prime minus T1. Yeah. So T2 prime minus T1 is 288. So if you solve this equation, you will get directly T2 prime. T2 prime comes as 549.6 Kelvin. Now I know T2 prime, so I can directly calculate my compressor efficiency. So work done by the compressor, compressor power. So work done by the compressor is what? So this is an isentropic process. From 1 to 2 prime is, so it is already told that for this particular process, for the compression process, the Cp is given. So you directly use that Cp times your delta T. So if it was isentropic process, then instead of T2 prime, you will be having T2. But anyways, now we already calculated T2 prime, so you just substitute the values. It will be 1.005 and T2 prime is 549.6 minus T1 is 288. So this is done. Now what is asked is the net work output, the net power developed, the net power developed by the unit per kilogram per kg per second of the mass flow rate. So how will I do that? So okay, even before that, we are asked to find the pressure and temperature of gases entering the power turbine. So we determine only state 2 prime. We are yet to determine what is state 3, state 4 and all this stuff. So we need to calculate state 3. How do I get state 3? So what is told here is this high pressure turbine is actually used to, the compressor is driven by the high pressure turbine. So whatever is the work output of the high pressure turbine should be equal to the work done on the compressor. So from there, if we equate that one, so we'll be able to calculate the state 3. So it is given HP turbine drives the compressor. So what does that mean? That means work done by the compressor should be equal to work done by the high pressure turbine. So that means we have Cp gas times, for the high pressure turbine, that will be T3 minus T4, T3 minus T4 prime should be equal to the work done that we have calculated before, 262.9. 262.9. So out of T3 and T4, so maximum temperature is reached at 0.3. So it is already given that the maximum cycle temperature is 610. T3 is the maximum temperature. So we have T3 to be 610 Celsius. Or if you convert it into Kelvin, it will be 883 Kelvin. So now you know T3, so you can substitute that in the above equation to get T4 prime. CPG is given as 1.15. That is 64.4. So we have T4 prime also. And now the power turbine, temperature of gases entering the power turbine 654.4 Kelvin. That is T4 prime. And we are also asked to find the pressure of it, the pressure of the gas that is entering this one. So temperature is we know. So how do we calculate pressure? Again, we know the process. 3 to 4 is isentropic process, so we can calculate the pressure directly. So, but for that I need to calculate T4 first. If I know T4, then I can use isentropic relation. So how do I calculate T4? Again, we use the relation for the efficiency of the turbine. So we have efficiency of high pressure turbine as what happens in case of actual process, my T4 prime divided by isentropic process. So the eta is given as 0.85. T3 we already know, that is 610, or let's put it in Kelvin, minus T4 prime, which we have calculated just now, divided by T3 minus T4. Now if we solve this, I will directly get T4 as 614 Kelvin. Now once I know T4, we can directly use isentropic process relation. 3 to 4 isentropic process. So we'll directly use the relation T3 by T4 is P3 by P4 to the power gamma minus 1 by gamma. So from this we need to calculate P3. So you know all the values. P4 we know 1.01 bar, T3 by T4 we know, T4 we know, T3 we already calculated as 883 Kelvin. So all we need to do, gamma is also known. So we can directly solve for P3 directly, and the P3 value comes out to be around, sorry, P3 is already known as 7.07 bar. We need to calculate P4. P4 can solve directly, and then that comes out to be around 1.66 bar. So this is the first part of the question. We are asked to find the intermediate pressure and temperature. So this is 7.07 bar, this is 1.01 bar, and the intermediate pressure we got nowhere as 1.636 bar. Now the next part asks you to find the net power developed per unit mass flow rate. So this is again straightforward. So what is the net power rate? So what is there are two turbines. So this is also generating power. This is also generating power. The power generated by the first turbine is used to drive the compressor. So from there you will not get any work output. So the net work output is only from the turbine part. So how do I calculate the power output? So work done by the low pressure turbine will be the net power output, and that should be equal to, since it is per unit mass flow rate, I am directly writing in terms of the enthalpy changes. So the enthalpy is changed from 5 prime 4 prime to 5 prime. That is the actual work done. So this will be H4 prime minus H5 prime. And how do I do that? We'll use the slip relation, but it will be the after combustion, so it will be the gases, combustion gases, times T4 prime minus T5 prime. So out of this, I know CPG. CPG is already given as 1.15. All I need to know are T4 prime and T5 prime. T4 prime we have calculated before, that is 654.4 Kelvin. Now I need to determine T5 prime. So how do I calculate T5 prime? So 4 prime to 5 is an isentropic process. So first I will calculate from this, and then I will use the isentropic efficiency of this turbine to calculate the temperature at 0.5 prime. So the process is again straightforward, just as we have done before. The first thing is your isentropic process. Which process is isentropic? It's from 4 prime to 5 is isentropic. So I'll write my relation. T4 prime by T5 equals to P4 prime by P5 to the power gamma minus 1 by gamma. Again, which gamma you should be using here? The gamma should be for the gases, because this is after the combustion. So this is air, so here you should be using a gamma of 1.4, but after combustion you'll have those gases. So you should be using Cp or gamma, whatever of the gases. So the gases one is 1.333. So we will use 1.333. So solve for T5. So what are the values? We already know T4 prime. T4 prime is 654.4 Kelvin. So I'll directly write it. T5 is T4 prime 654.4 times P5 by P4 prime. P5 we already know as 1.01 divided by P4 prime we have calculated as 1.636 whole power 0.33 by 1.33. And if you solve this, we get T5 as 580.6. Fine. Now we have T5. The next thing is to calculate T5 prime. So there again we use the efficiency of the turbine process. So efficiency of your low pressure turbine is, since it is a turbine, it is the actual by ideal. So T5 prime minus T4 prime, T5 prime minus T4 prime. This is the actual process divided by the ideal process. The ideal process is T5 minus T4 prime. So eta is given as 0.85. T5 prime we have calculated before. Sorry, T5 prime is what we are trying to calculate. So T5 prime minus T4 prime we have calculated before as 64.4 divided by T5 we already know, which we have calculated just now, minus T4 prime. So from this you can directly get T5 prime by 91.7 Kelvin. Now I have T5 prime, so net power output is straightforward, which we have already known before. So W low pressure turbine is CPG is 1.15 times T4 prime is 64.4 minus T5 prime is 591.7. So this is 72.1 kilowatt. Work ratio is again straightforward. We have already known all the enthalpies, so this shouldn't be a big problem. The work ratio will be W net divided by W gross. The network output is what we have calculated just now, 72.1 divided by gross power output is the power output by the high pressure turbine as well as the low pressure turbine. This is the low pressure turbine plus the power output by the high pressure turbine, which we have calculated before. So that is equal to the power of the compressor, that is 262.9. This is 0.215. Work ratio is done. And what is the thermal efficiency of the unit? How do we calculate thermal efficiency? Thermal efficiency is what? It's again whatever is your net work done divided by whatever is the net heat you supplied. So W net we know as 72.1. What is the net heat supplied? The net heat supplied, where are you supplying the net heat? In this combustion, this is where your heat is supplied. So Q in is the heat is being taken by the air. So this should be Cp air times the change T2 minus T1. Sorry. Uh, sorry. I think I messed up here. This combustion, this is your compressor. Yeah. So what is happening? So from 2 prime to 3. So this will be 3 minus 2 prime. CPA we already know 1.005. Sorry, inside the combustion times T3 minus T2 prime. Yeah, now we have the heat, now we have the work output, so we can directly calculate the thermal efficiency. 72.1 divided by 383.4. So I think I used wrong unit here. And this comes out around 0.18. 0.188. Okay. Yeah, that's it. So we have solved problems on Rankine cycle. We also solved problems on refrigeration cycle, and then we have solved one problem on Brayton cycle. Are there any questions? Yeah, if there are no questions, I think we can end the session for today. And best of luck for your exams, who is attending for the exam. And thank you all.